Hi, what's up guys? Today's video is going to be a lesson on Le Chatelier's principle for the Chemistry 30 equilibrium unit. So, in this unit we're going to be outlining the basic principles of equilibrium, and we're going to talk about Le Chatelier's principle and the different stresses that you can apply to equilibrium to shift it in different directions in a reaction. So what is equilibrium? So a dynamic equilibrium is when the forward reaction rate is equal to the reverse reaction rate. So it's important to note that it's talking about the rate and it's not talking about the volume of like reactants and products, because as long as the rate at which these reactants and products change is equal, that means it's at dynamic equilibrium. As long as there is a constant temperature and a closed system, that means a dynamic equilibrium can occur. If both or either of these factors are not present in the reaction, then dynamic equilibrium can't occur. So, another important thing to note right now is that Kc value is always constant, no matter what kind of stress you apply to the reaction, unless the temperature is changed. So Le Chatelier's principle is where a system at equilibrium is subjected to a stress. So when this happens, for example, you have like A in equilibrium with B. So say you increase the concentration of A. If you do that, then the system will try to counteract this increase in A by shifting the amount of concentration of A to create more of product B, so that equilibrium is created again and the concentration is not differed. So there are four main factors that affect equilibrium. So one is easy to talk about because it's just the reactants that we use in the reaction. So as long as we use like A plus B has an equilibrium with C, then that's all we have to worry about, because these three are the elements that we used in the reaction and these don't change, so equilibrium will not be affected. So concentration. For example, we have this reaction. So if we added more NO, so increase NO, that means the reactants in this equation is going to be more than the products at equilibrium prior. So that means there's too much on the reactant side, which means they'll try to react towards the product to shift the equilibrium back. So that means the rate of forward reaction is increased to try to use up this excess NO, while the reaction that's backward is still the same. So at this new equilibrium, the NO will have a net increase, the O2 will have a net decrease, and the NO2 will have a net increase. So we can also draw that reaction with the equilibrium shifts on a graph. So this is going to be concentration, the y-axis. X-axis is going to be time. We start with the same amount of O3, A, B, C. The one that we add, like physically add, it goes right up. The one that is on the side of the one that we add, it gradually starts moving down. This one, after it increases to a spike, it will gradually level out back to a new equilibrium. And C is the one that is on the other side, so this is the reaction that I'm talking about here. A plus B to C, it's gonna gradually increase as this decreases. So temperature. Say we have A plus 100 joules goes to B. So here you're putting energy into the system. This means that the reactant side has more energy put in than what is given out on the product side. So that means this is an endothermic reaction, which means that the system gets energy taken up. So here, if you increase temperature, increased, that means to counteract this change, the equilibrium will try to shift away from where it's added to the other side, which increases B, while A decreases. So if you drew this on one of these graphs again, A, B, so A, B, A gradually drops and B gradually increases. It would be the same if we looked at it in a exothermic reaction, because we put in these two, which is less heat than what came out. So that means if we, for example, increased B, this would decrease since it's on the same side as B. This would increase and this would increase. So what this would look like was gonna be A, B, C. So A is gonna go, sorry. So A is gonna level at equilibrium, slowly drop down. B is gonna slowly increase, uh, and C is gonna slowly increase. So as you can see, when you increase temperature, it's never gonna have a spike, because a spike only occurs when either one of the elements is added, or if you add something else that isn't part of the reaction in, for example, like D minus, and say A and D minus react together, then you would see something like a downward spike, which gradually comes back up, because the D increase will bring down the A increase, the A concentration quite drastically. So pressure is a special case in gases where, for example, you have 2A plus B goes to, let's say, 2C. So count up the total number of moles on each side. So the left side has a total of 1, 2 A's and 1 B, which is a total of 3. Here there's a total of 2. So that means when pressure is increased, it will shift towards the product side. If pressure is decreased, which means volume is increased, then it would shift this way. So let's just write that out here. So pressure increase, it would go that way, and volume increase, which is the same thing as pressure decrease, will go towards the reactant side. So the last thing to look at is the equilibrium affection by catalysts. So catalysts are special because there's no effect on equilibrium. Point, because if a catalyst is added to the reaction, then it would mean that the products and the reactants reach equilibrium faster, but they both increase in rate at the same magnitude, which means that it would only speed up the process which equilibrium is reached, but it won't add like a specific product which shifts the equilibrium to the certain side. So let's try a practice question right now. So I'll just type out the reaction that we're going to look at. It's going to be N2 gas plus 3H2 gas goes equilibrium arrow to 2NH3 gas plus 91.8 kilojoules. So part A of the question asks for what happens if you increase nitrogen gas. Part B asks if you add heat, and part C of the question asks if you decrease volume. So if you increase nitrogen gas, so increase, that means that the system will try to balance itself out again by counteracting this, and to increase by using it up in the forwards reaction. So it's going to shift to the right. This means that the NH3 is going to increase as more of this N2 is used to create the NH3, and this H2 is going to be decreased as the rate of N2 to NH3 is going to be the main reaction increase. So if we drew that, it would look like N2, H2, NH3. N2 is going to spike up, H2 on the side of the increase is always going to go down gradually, and NH3 is going to gradually increase. So let's just label that as A. So B, if we add heat, heat is here, increase that, that means it's going to shift to the reactant side. NH3 is going to decrease, H2 is going to increase, and N2 is going to increase. So let's just continue that from here. N2 increases gradually, H2 increases gradually, and NH3 is gonna decrease gradually. Now let's look at part C. So if we decrease the volume, let's count up the moles. Actually, let's just erase some of this because it's getting pretty messy. So 1 mole here, 3 moles here, 4 moles on the reactant sides, and 2 moles, just this, on the product side. So that means if you decrease volume, that's the same thing as increase of pressure. So that means it's going to shift towards from the higher pressure side to the lower pressure side, which means it's going to go this way. And that means more NH3 is going to be produced, and since the shift is towards the products, then these are going to start decreasing. So let's look at that. N2 is going to decrease gradually. H2 is going to decrease gradually, and NH3 is going to increase gradually. So that's it. That's it for today. I hope you enjoyed and learned something from this video, and if you have any more video suggestions, please let me know. And if you have any feedback for how I should improve these daily uploads, because I'm going to be uploading daily, then let me know as well. Thanks for watching.